3 full days of just only doing chemistry, you will understand half of what we understand.
Yeah. So unit 2 is probably the most challenging unit in the whole subject, whole curriculum. Unit 3 is the potpourri unit, and to get you caught up from yesterday, Unit 3 is a potpourri unit. It's basically a little bit of everything, and it's 20% of the entire curriculum. So there's things that are in molecules, things that are out of molecules. It even talks about electrons, which we're going to talk about today. So anyway, to bring the 3 up that we're not here. Did you go get your stuff?
Yeah.
Yeah, good idea. I waited for 5 minutes and I locked the door. So it was like, no one's showing up. I'm just going to lock the door. So a solid compound is most likely going to be an ionic compound, positive, negative, or a molecular compound held together with intermolecular forces. So again, I talked about this. Sugar easily dissolves. Okay, those sugar crystals break down when the individual sugar molecules separate. Nitrogen basically forms a gas at about -70 Celsius, and carbon dioxide forms a gas about -40 Celsius. So these are very weak bonds. They're specific bonds between molecules. On the other hand, you have network solids. These are called covalent network solids, and they're gigantic molecules. They make giant molecules. Diamond is one of them. If you have a diamond, it is one giant molecule. No joke. It's a molecule made out of about 1/10 of a mole of carbon atoms. One gigantic molecule. So silicon dioxide, silicon carbide, and then graphite and graphene and nanotubes, those are all one big molecule. They're all held together covalently. And this is what diamond looks like. You have diamond, basically every carbon is attached to 3 others, and it makes this crazy structure that is exceptionally rigid. So that's why diamond is the hardest, most naturally occurring substance on the planet, because of all those carbons. So, and then if you get sheets of carbon, you get graphite, and if you get the diamond structure, but only a couple atoms thick, and you roll it out, you get graphene, which you roll up into a tube to make carbon nanotubes, and you get some pretty cool properties with that. But those are covalent network solids, exceptionally strong. None of these will dissolve in water. There simply isn't enough energy in those water molecules to break them apart. Make sense? All right. So again, if you hear covalent solids or network solids, or even better, covalent network solids, you're talking about gigantic molecules. A diamond is one gigantic molecule. Okay. Give me a thumbs up if this makes sense to you. Cool, moving right along. We talked about metallic bonding. Again, I want to skip over that to get to this. But again, for Brett's benefit, when you have metallic bonding, all the protons are fixed in place. The electrons just move through the electron sea. There are 2 types of alloys we talk about. Substitutional alloys happen when you have a D-block metal melted into a D-block metal. The atoms are about the same size, and they still experience the electron sea. That's a substitutional alloy. For the most part, the properties don't change much. An interstitial alloy is what happens when you put a non-metal into those metals, like steel. There's a bunch of carbon atoms that dramatically increases the rigidity of the alloy. Okay. And we talked about gas laws. We talked about all these gas laws. This is all a review of last unit. Pascal's principle, the pressure is exerted uniformly everywhere, and pressure is force over area. Dalton's law tells us that if you have a big mixture of gases, the total pressure is the sum of the individual pressures. Boyle's-Charles d-Luc-Sachs becomes a combined law, and that happens a lot. Combined law is usually expressed as P1V1 over T1 equals a constant, or P1V1 over T1 equals P2V2 over T2. And then Graham's law just says that if you have 2 samples of gas, then they have the same kinetic energy. The more massive molecules will move faster or slower. Like, what? We have to pay? I was paying attention just now. The more massive particles move slower, and the less massive move faster. If you like to see it visually, it looks like this. You have 2 samples of gas. One is 1/2 mv squared, and the other is 1/2 mv squared. Okay, and then real and ideal gases. Real gases bounce elastically. They bounce like billiard balls. Ideal gases bounce like billiard balls. Real gases bounce like footballs. And when does an ideal gas act like a real gas? When does a gas behave like a real gas and not an ideal gas?
High pressure, high temperature.
High pressure, low temperature, which is basically high density. Anytime the molecules are close enough together that they start to attract each other, that's when you move away from ideality. So all you need to know in May is what causes gases to move away from ideality. High pressure, low temperature when they get close together. You don't have to do any math with van der Waals equations. You keep using the ideal gas law. Okay. Does that make sense? So all the gases, keep using the ideal gas laws. All you need to know is what causes something to move away from ideality. Cool, then we talk about vapor pressure, and I was gonna do the syringe, America was gonna tell me to do the syringe, and I don't have my syringe, but I'm gonna do it because it's cool. So, it's really simple, I just gotta get a syringe. I seem to have misplaced my one I picked up yesterday, so I'll just get my, here we go. Put some water in my syringe. I'm going to nuke it just a bit. So what does happen with liquids is the molecules of liquid, there are a few molecules that are pretty high in energy. This diagram is actually a pretty good one. So this would be like room temperature water, where there's just a tiny little triangle that have enough energy to leave the liquid phase and form the gas phase. You warm it up, and now that triangle is a bit bigger, there's more gas molecules that have enough energy to leave the liquid phase and enter the gas phase. And the reason liquids don't just evaporate all out is because there's atmospheric pressure pushing down. If you take away the atmospheric pressure, what does the liquid do? It boils. Yeah. Take away the atmospheric pressure and the liquid will boil, which is what I'm going to demonstrate in just a little bit. When you rush, that's when accidents happen. Alright, so I've got some water. You can see from the condensation it's fairly warm. It's not boiling though. I can put my hands in it for a little bit. So I get some water in here. You guys hopefully remember this in the last year. There we go. We've got a tiny bubble. We put a cap on it. Is it boiling? No. Is the water boiling? No. It's like 50 or 60 degrees. Is it boiling now? Yeah. How come it's boiling now?
Because you took away the atmospheric pressure.
Yeah, take away the atmospheric pressure. Take away the atmospheric pressure and there's nothing to keep the, or there's less to keep the gas or the liquid particles entering the gas phase. Hey, when you boil a pot of water, what are those bubbles?
Water vapor.
Water vapor, yeah. When you boil a pot of water, it's not air leaving the water. It's not like dissolved oxygen. No, it's water vapor. It's water vapor that is forming at the bottom of the pot, bubbling through the pot of water. All right, now we can move on to other things. Not new because it's all review. Okay, so we talked about these last year mixtures and solutions. You have a solution, a colloid, or a suspension. Whoa, that was fast. Okay, that was, okay. All right, so the words you need to use are homogeneous and heterogeneous. Homogeneous means one phase. Heterogeneous means obvious phases. Say, like homogeneous, Kool-Aid's a homogeneous mixture. Heterogeneous, salad dressing is heterogeneous. Be like, there's definitely some stuff in there, unless it's like pure mayonnaise, gross. But if it has obvious phases, it's heterogeneous. If it's only in one phase, it's homogeneous. Suspensions have very large particles that do not settle out. Solutions have small enough particles that they do settle out, and colloids are right in the middle. And then the Tyndall effect is what we can use to determine one from the other. If you have a light beam or a laser or something traveling through a solution, it's not going to be seen in the solution. It will be seen but pass through a colloid, and it'll pretty much be blocked in a suspension. So that's how you can tell a colloid from a solution. Hey, for Brett's benefit, what is the phrase we use to talk about whether something is soluble and what causes something to be more soluble than others? Why are solids more soluble at warmer temperatures?
I remember you telling us yesterday, and I also remember thinking I was going to forget it really quickly.
Mission accomplished. Exactly. The phrase we're using is solvent-solute interactions. Anything that increases the solute-solvent interactions will increase solubility. So the reason solids increase their solubility with increased temperature is because the particles hit more often, and that increases solute-solvent interactions. Make sense? Okay. The reason that a powder will dissolve faster than a chunk is because there's more surface area, so more solvent-solute interactions. All right. And again, the solvent is whatever there's more of. Like in air, nitrogen is the solvent. In gold, if you have 14 karat gold, then gold is the solvent. If you have 10 karat gold, gold is not the solvent. Because the carat system is based on parts of 24. So if you have 14 karat gold, that's 14 over 24 parts gold, and 10 over 24 parts something else. If you have 10 parts gold, then maybe tin is the solvent, and gold's actually the solute. It's 10 of 24. Words we use are miscible and immiscible. Miscible means it can mix. Immiscible means it cannot. Oil and water are immiscible. Sugar and water are miscible. Alcohol and water are miscible. And then again, remember intermolecular forces. That's pretty important. And then saturation. If you have a saturated solution of an ionic crystal, let's say I have a beaker of sodium chloride, and it's saturated, how do you know if it's saturated? You don't taste it, but how do you know if something's saturated? Yeah, so you put a salt crystal on the surface, it's going to fall right down through. Okay? If something is unsaturated, it will dissolve. If something is super saturated, it will grow as more crystals stick to it and come out of solution. If something is saturated, it's going to fall right to the bottom. Is that crystal actually just falling right to the bottom? We talked about this last year. If you have a saturated salt solution, you take a sugar crystal or salt crystal, you drop it into solution, it looks like it's falling to the bottom. Is it actually just falling to the bottom? Is it not doing anything as it falls to the bottom? When you are at saturation, I don't think I need these anymore. Erase these. When you are at saturation, this equilibrium expression applies. So just keep with my analogy. NaCl solid is in equilibrium with Na plus, which is aqueous, and Cl minus, which is also aqueous. Okay? That's the equilibrium. So in a saturated solution, you're holding as many ions as you can. If you put a crystal into solution, what's happening is that crystal is dissolving and reforming, and dissolving and reforming, and dissolving and reforming, and dissolving and reforming. So if you had your beaker of water, and you put your crystal in, if you were to try to track those those ions, they wouldn't go straight down. They would go, they'd spread out entirely. But there would still be a crystal at the bottom. Only that crystal at the bottom would be made of a mixture of the original ions and ions that were already in there. Does that idea make sense? Okay. So it's going down, it's dissolving, other ions are coming into form, those are dissolving, other ions are coming, and that's constantly happening. There's a good PET simulation that actually showed that, but oh well. Hey, does that idea make sense? Bringing it right along. Okay, so solubility, again, whatever increases solvent-solute interaction. So how does solubility of solids affect temperature? Or how is it affected by temperature? As temperature goes up, solubility goes up, okay? Because you have more solvent-solute interactions. As gases increase temperature, something else happens. As gases increase temperature, their solubility goes down. This is why when you pop open a 2-liter bottle, it's better if it's cold. You're going to lose less CO2. If you open your 2-liter bottle at room temperature, it's going to go flatter a lot faster. And the reason that is with increased kinetic energy, you've actually reduced the London forces, increased the kinetic energy of the particles, and the particles will fly away. And there, bye-bye. Okay, and Henry's law. Henry's law is a linear relationship that states the more you increase pressure, the more gases you can get into solution. Pressure does not affect solids at all. It does affect gases. So as you double, it's a linear relationship. So if you double the pressure, you'll double the solubility of the gas in the liquid. Which is why there's that gigantic aluminum tank that sits outside of an In-N-Out burger. It's at high pressure. If somebody poked a hole in it, it would rush. Carbon dioxide would rush out. It's at high pressure because it has to push the gas molecules into solution. That's supposed to be an equilibrium sign. It's supposed to be an equilibrium sign. Okay. Does this make sense so far? We good? Okay, any questions? If you have a question about this stuff, wave your hand around or just stop me. If you're good, give me a thumbs up. Cool. Okay. Distillation. Wow, that was fast. I thought there would be another slide. Distillation. Distillation, just like in the video, is the separation of substances based on their boiling point. And fractional distillation is a complex way to heat up a bunch of stuff and then allow it to cool down. So what happens in these giant towers in Texas and Southern California is they take a bunch of crude oil, yucky black crude oil, and they heat it up without oxygen anywhere. It's important you actually suck all the air out. So you heat it up, or you flood it with nitrogen, or hydrogen, or argon, but something that won't burn when it gets really hot. You heat it up, and it starts to boil, and the vapors come up. And then the things that will condense at 1,000 degrees Fahrenheit, this is an example, they are taken off, like little trays that come off, and then diesel oil, the vapors come up, they get cooler, and diesel oil condenses, the vapors come up, and they get cooler, and kerosene condenses, vapors come up, they get even cooler, and naphtha condenses, even cooler, gasoline comes off, and then anything that's left is natural gas. This is how fractional distillation works. You heat up a pot, and then the vapors come up, and as they cool, they start distilling into a liquid, and we collect those liquids. The things that have a higher boiling point will condense, then the condense, and the ones condense, and the ones that stay gases will just be natural gas. We'll collect those. Then we pump them into your car or an airplane.
Diesel's pretty hard out there.
I'm sorry?
Diesel's pretty high.
Yeah. And diesel has a pretty high boiling point. Yeah.
Is that the end of the refining process, or do they do more after that?
Oh no, they have to do it multiple times.
Oh, okay.
Yeah, you have to do it multiple times. So this is the dramatically reduced version. But yeah, so this will come off, and they'll have to refine it. This will come off, they'll have to refine it. This will have to come off, they'll have to refine it. Because these hydrocarbons, they're called hydrocarbons, they mix pretty well with each other. So what comes off here isn't 100% kerosene. It'll be like 80% kerosene. It'll have some naphtha and some diesel in there. So yeah. Same thing with when we distill booze and moonshine, because water and alcohol mix so well, ethanol mix so well together, that when you distill moonshine, even at 70 degrees, even though water's boiling point's 100, you're still going to have a little bit of water in your moonshine. You know all about that.
That one was
So-
okay?
Distillation basically is boil it all and let intermolecular forces sort them out. Okay. Boil it all and let the intermolecular forces sort them out. So which type has the higher intermolecular forces, the bottom or the top? The stronger intermolecular forces, the bottom or the top?
The bottom.
The bottom. We have the high intermolecular forces, large carbons. Now realize these are all non-polar. They're all non-polar, so if they're non-polar, what are their intermolecular forces? London forces, yeah. If they're all non-polar, then their intermolecular forces are London forces, but you have gigantic carbons down here, big long chains, so they have stronger London forces, and up here where you have the methane, ethane, and propane, then you have very, very weak London forces. Okay? They're all non-polar, so they have to have London forces, not dipole-dipole. Give me a thumbs up if this makes sense to you. Cool. Well, this is vapor distillation, like this is the distillation that was in the video. So vapor distillation basically is you target one thing at a time. So you heat up your stew, and then the vapors come up, and this is your target temperature. If you're shooting for ethanol, you want to set this about 75 degrees Celsius. So it's going to be boiling, but mostly only ethanol is going to be boiling. And then you collect it, the condenser water goes in. I love these things, they're so cool. Maybe I'll see if I can get some for next year. So the water comes in, cools the vapor turns into a liquid, go ahead. And then it goes into the receiving flask. And the stuff that goes into the receiving flask is called the distillate. Yes?
Back to the wonderful thing. You gave us like, I think on one of the packets you gave us, it was like a carbon, and it was 4 chlorines and the carbon, 2 hydrogens. And which one was stronger?
I don't remember the exact exercise, but the carbon, the carbon with 4 chlorines would have a whole bunch of electrons. So even though it's non-polar, it would have pretty decent London forces.
So there's 2 men, and there's like more London forces, like, and that makes us stronger than the dipole.
Exactly. So in general, apples to apples, dipole forces are stronger than London forces. But you can have stronger London forces than dipole forces. So if you're talking about 2 molecules of similar size, the dipole-dipole forces, or the hydrogen bonding, will be stronger than the London forces. But for big molecules that have a lot of electrons, they can have strong London forces, like wax. Wax is a great example. It's a solid room temperature because it's got so many carbons, it's got so many electrons. So yeah, I think that carbon tetrachloride is a liquid at room temperature, and it has very strong London forces. Okay. Are we cool with this? Give me a thumbs up if this makes sense. Hang in there, John. I hate talking. I know, me too. We're almost done. There's not a lot left. Chromatography. We still have to talk about quantum though. That's fine. So chromatography. We've done chromatography already. Again, I'm writing these so they're complete. So next year we'll actually do the units in order. Get the summer slide. So we did chromatography. We talked about chromatography. This is the chromatography you did with strips, paper chromatography. HPLC is high pressure liquid chromatography, and this is gas chromatography. You're going to encounter these when you go to college. They all work exactly the same way. They have a stationary phase, which gets in the way, and a mobile phase, which goes through the stationary phase. And the extent to which the polarity of the mobile phase and your sample mix is where they show up. So